Now let's talk about some more properties of light. Oh, I gotta bring my marker back up. So, first we're gonna draw a light wave for us to label. So we're gonna go like this. And this is gonna be my amazing light wave. And through here, we have the 0 point. So the idea of this line is that represents what zero energy would be. So the first thing to note we're going to use in terminology is sometimes we'll talk about nodes. These are going to be places, I'm drawing some dots there now, where the light is considered to have a value of 0, however we're measuring it, 0 displacement. So these are points where it doesn't have any value. It's not up or down. So that's going to be called a node, and we're going to use a node as a term in the next few definitions. So we have amplitude. This is related to the height of the wave, either from node to crest or node to trough. So a crest is going to be the top of the wave. The trough is the bottom of the wave. So what that means, if you draw a line from here to here, that is going to be the amplitude. You can also draw it from here to here. And because of how light waves work, the amplitude is going to be the same from the crest to the node or from the node to the trough. These are going to be the same thing here when we're looking at a wave like this. It's meant to be symmetrical here. The amplitude is going to determine the light intensity with light waves. So it helps to make it more intense. It's going to have a higher amplitude. So it'll be a brighter light, for example. Now another term we're going to use is called the wavelength. We use this variable here, lambda, to represent it in equations. So when you see this in an equation later, just know it means wavelength, and we say the lambda to go with it, as it's a Greek letter. This is the distance from one crest to the next, or one trough to the next. Those will also be the same. So for example, if I go here to here, this is one wavelength, or the distance our surfer had to travel to get from one top of a wave to the next in our introduction. Another property we're going to talk about sometimes is called the frequency. For this, we use the variable nu, which when I write it, it's going to be a bit like this. Like it looks kind of like a V, but there's a little bit of curve in it. So what frequency represents is the number of waves that pass a single point in a second. So for example, let's say I take this point right here, I made a dot for it, and I were to let the light wave travel for a single second. However many waves pass that point, that would be the frequency. I think this is the hardest one to imagine because when you look at pages in a book, the wave doesn't move. But remember, we're drawing something on a piece of paper that's stationary, but it's not actually stationary. Light travels to you at the speed of light. It goes really fast, like we talked about in our example problem. The light is traveling really fast, so a lot of times your frequencies, depending on your wavelengths, might be really large numbers. You might have 10 to the 10th waves pass a point per second. It's okay for frequencies to be huge. On the other hand, you will have some types of waves where the frequency is really small as well. Maybe the wavelength is a mile long. Something like a radio wave where you start getting huge distances. Well, then it still takes it a while to travel, so it's not going to be a huge frequency for those. So know that frequency can vary massively, as well as wavelength. Wavelengths can be really tiny or they can be long. I mentioned that both of these can vary so much because I know in a lot of problems, students you may be more used to working with numbers like, oh, this weighs 100 grams or 10 grams or 1,000 grams. But then when you see a number in your calculator like 4.25 times 10 to the minus 19 meters, you might think, oh God, I've got to be wrong. This number is too small. This can't be right. So with these, you can end up with incredibly large or incredibly small numbers. That's okay. And then one last thing that I can't put directly on here but is related to the wave is the total energy. For this, we use the variable capital E. This is going to increase as the amplitude of the light increases and as the frequency of the light increases and just represents what's the total energy associated with the light wave. This becomes relevant because we start using light and we wonder about how much energy it's able to transfer something, or if we put energy into something and it ends up releasing light, how much energy did it need to do that? So we'll talk about energy a lot as it relates to light, and it's related to both the amplitude and the frequency of the light. So how are these properties related to each other? So the frequency and wavelength of a light are directly related via this equation. C equals wavelength times frequency. So remember, that is the speed of, I've got it written right there. The speed of light equals the wavelength, that's the lambda, times the frequency, that's the nu. And the speed of light was the c. So what this means is that because the speed of light is a constant, as long as we're working in a vacuum, that means the other two variables have to be inversely proportional to each other. Since c can't change, when wavelength changes, frequency has to. And when frequency changes, wavelength has to. So the way this works is when wavelength, that's our lambda, goes up, frequency has to go down. That's supposed to be a down arrow, not another frequency. The inverse is also true. If wavelength goes down, frequency has to go up. And you can think of it the other way. If frequency goes up, then our wavelength goes down. If our frequency goes down, then our wavelength goes up. As long as you're not changing the speed of light by changing the medium it's traveling for, you cannot disobey this law. So these relationships have to happen. You can't change the wavelength without changing the frequency. You can't change the frequency without changing the wavelength as long as the speed is constant. So I wanted to point out something about this electromagnetic spectrum we're talking about. So we've been talking about light and how it travels. And a lot of times you may think of light mostly as the part you see with your eyes. But that part only makes a tiny itty bitty range between 400 to 700 nanometers, which also means it's around the area of 10 to the negative 9. Remember that for 1 nanometer is 10 to the negative 9 meters. And I'm mentioning this because it's going to make sense with the spectrum I'm going to show below. So here we have an idea of how the light can look at a lot of different wavelengths, not just that little 10 to the minus 9 range. So you can have light waves that are on the order of buildings in size of how long their wavelengths are. For example, a radio wave can be as big as like 10 to the 3 meters for a single wave to pass. On the other hand, you start getting small fairly quickly. When you get to microwaves, like the ones you can use to heat up food that can help transfer thermal energy by exciting water molecules and making them vibrate, those get pretty small. They're down to 10 to the minus 2 meters, or 1 inverse centimeter. And then you get down to infrared light, where we're starting to get even smaller, 10 to the minus 5 meters. And then we get to visible light, and as we keep getting smaller and smaller, we're going to get quite little, down to the size of atomic nuclei when you get all the way to gamma rays at 10 to the minus 12 meters. So the idea behind this, I really like the size scales to get an idea of, as this goes, light has a lot of different varieties. You can have light that is as long as a building, or it can be as long as an atomic nuclei in the middle. So you'll also notice that the frequency range changes along with the wavelength. So for example, radio waves at 10 to the 3 meters are going to have frequencies here of around 10 to the 4. Whereas you get to somewhere like a gamma ray at 10 to the minus 12, it's going to have a frequency around 10 to the 20th. I think that's helpful to keep in mind as well, is that helps show that relationship. So as our wavelength got smaller, our frequency went up. And as we got really long wavelengths, our frequency went down. The other property to mention with waves is the idea of interference. So since it's a wave, if two light waves interact with each other, they're going to interfere. Kind of like if you've ever seen two water waves and they're close to each other, if they were to hit each other, then they interact with each other. They don't just stay separate from them. So let's take the example of constructive interference. What the word constructive means is the way the waves are going to line up is you're going to have two waves, and they're going to match so that when they hit each other, they start off looking like this. Pretend these are the same. I didn't do it perfect. Okay, we're going to pretend that everyone's like this one, where the crests are perfectly matching. They're not here. I know the bottom one's a little off. If they exactly matched, then they would completely constructively interfere. What it means when we say that the crests and troughs exactly match is that they are in phase. So what they do is they add together, and they make a big wave. That is the addition of both crests and troughs together. Now, we can also have destructive interference. I wrote that too big, so I'm going to erase this one, and we'll make a new one for that one. So now our destructive interference, on the other hand, I thought I had a little more room than I did, where we do that. But now, it's going to start at a different place. It's going to start down here, and then it's going to be at the top, up there, then the bottom. Did I do this badly? No, that's right. Bottom, top, bottom. It's probably being bad at drawing, sometimes you're not sure if you're matching things up right. So here, the exact bottom of my wave matches up with the top of this one. And here, the bottom and the top are at the same place again. So what that means, if we're able to get these so the bottoms and tops are opposite each other, when we try to add them together, we're just going to get a flat line. There won't be any wave at all. If they were different size waves, then we would just get a smaller wave as they add. Now, for us, we're going to look at examples where they perfectly constructively interfere or perfectly destructively interfere. Those are the easiest to work with conceptually. As you might guess, you can interact two light waves together that have different frequencies, so that sometimes the top and top match, sometimes the bottom and top match. Then you get much more complicated shapes. So that's something you will do if you stick with science in much later classes, but right now we're just going to stick with what happens when they perfectly match or they perfectly don't match. They're either completely in phase, completely out of phase. So our in phase increases in size by doubling, by adding them both together if they're the same size. And our smaller, and our ones where they're out of phase, they turn into no wave at all if they exactly match and are the same size. So that's the types of things our waves can do. Now let's do a little bit of math with our light now. So we're going to do some calculations using that light equation we looked at a couple slides ago. So before we do an actual problem, I need to make a note on units. So frequency, remember that's our symbol nu, is often going to be listed in a unit called hertz. That's used the term Hz. What that means is units of something per second, which you can also write it as S inverse 1 or 1 over seconds. Make sure to pay attention to units that they're going to work out because your wavelength is often not given in meters, whereas the speed of light is. So you have to make sure when you put your equation, just like when we worked on density in a previous chapter, that the units work out. You can't just plug them into an equation and assume, oh, everything's good. So let's take an example problem that I'll work, and then we've got a follow-up one for you to give a shot to. So we're going to calculate the wavelength in nanometers of a laser light emitted from a laser pointer that has a frequency of 4.72 times 10 to the 14th inverse seconds. And I want the wavelength in nanometers. So if I'm going to do this, let me get my pen back. There we go. So we know the speed of light is equal to the wavelength times the frequency. I want to solve for wavelength. So I'm going to divide both sides by frequency. That'll make frequency cancel here. And I'm just going to write the wavelength on the left side is equal to c over the frequency. I just flipped the sides. I didn't change anything else. So now we're going to plug those numbers in because right now the units are okay. Speed of light is going to be meters per second, frequencies in seconds. Those will cancel. I don't have to do any conversions yet. I can convert it to nanometers at the end. So there's 3.00 times 10 to the 8th meters per second divided by the frequency of 4.72 times 10 to the 14th, and I'm going to write that as per second. We can see that we have the same thing on top and bottom, even though they're both in the bottom part here, because it's one of the numerator, one's the denominator, that works out. So when I do that, I'm left with meters, and I calculate that as 6.36 times 10 to the negative 7th meters. And if the problem didn't ask you for a unit, that would be a fine stopping point. To finish it, I'm now going to convert it from meters to nanometers. So 6.36 times 10 to the negative 7 meters. And I know that for every 1 meter, I have 10 to the 9th nanometers, because nanometers are smaller, so you need lots of them to make a single meter. The meters will cancel, and we multiply that out, and we get 636 nanometers. It's the wavelength of our light in nanometers. Let's take a look at a second example that you try first. So I want you to calculate the frequency instead of the wavelength this time. So what's the frequency of a light wave that has a wavelength of 350 nanometers? Give it a shot, and I'll try it in just a moment. Okay, let's look. So we know still speed of light equals wavelength times frequency, but this time I want to solve for frequency. So I'm going to divide both sides by wavelength, and that'll give me that frequency equals c over wavelength. Now, this time before plugging things in, speed of light is in meters per second, wavelengths in nanometers. I have to convert one of them. You could convert speed of light to nanometers per second, you'll get the right answer. But I'm just going to convert my wavelength to meters. Both are fine, neither is better than the other. We're going to try that again. In M, I have them next to each other. That was rough. So 350 nanometers, 10 to the 9th nanometers is 1 meter. We do the math with that, and we get 3.5 times 10 to the negative 7th meters. So now we can plug it in our equation. So frequency is going to be equal to 3.00 times 10 to the 8th meters per second divided by our wavelength of 3.5 times 10 to the negative 7th meters. We plug both those in, and we're going to get 8.57 times 10 to the 14th inverse seconds. You could also write it, the unit, in other ways. You could have written that as hertz. You could also write it as, I'm trying to put a comma there. Hertz. And you could also write it as 1 over seconds. Those are both fine. So this is the idea. We can use our equation, c equals wavelength times frequency. You know one, you can solve for the other.